Hi everyone, um, welcome back to Probability World. I see Ray here, Ian here, Lawrence, Jess. Uh, okay, let me know if you hear my voice clear and good. You can see my slides. Yes, okay, perfect. Um, so let's get started. Today I have some amazing stuff, useful stuff regarding um, probability and application of probability in electrical engineering and robotics, specifically using these topics that I'm gonna start today, factor graph. Um, however, we started that last time, and we want to continue from uh, that spot that we left that last time. We introduced the idea of probabilistic graphical models, and we made some like a building block, and we're going to continue and make in top of that. um, we we need to talk two things today. First, we're gonna go deeper into something called maximum posteriori, or MAP estimator. We're going to talk about maximum a posteriori, and after knowing maximum a posteriori, you can see how so many applications can fit in that modeling. It's kind of modeling, maximum a posteriori estimation. Probably we talked about that before too in a different way. Like we said, oh, we are finding posterior density. Posterior density is when we are talking about probability of some unknown given some measurements, some known information. So, and that's going to the Bayesian formula and can break down to prior information and the likelihood, and then we can solve that efficiently. We're going to talk about that today. And also we're going to go, last class we talked about um, actually graphical models. We said, so probability and the mathematical way of explaining probability is a little hard to figure it out and understand. But graphically, we can explain that maybe easier. So we start talking about Bayesian net or Bayesian network. We said conditional probability, joint probability like P of x1, x2, x3, and 4 can break down to product of conditional probabilities. Conditional probability of 1x given their parents. So that's going to give that idea to us. What about we just make all of this conditional probability as a graph? We explained that last class, and we said that graph is directed graph because it has parents and son and whatever child, and is a cyclic. It don't have cycle on it. Okay, that's gonna be a little trouble, and we're gonna today see if we can have different graphical models, and we have, and that is factor graph. We're going to talk that today. Okay, so let's get started. First, we're going to talk about maximum a posteriori estimator, MAP. Let's make this smaller. I think it's too big. Okay, no problem. Just want to see the picture here. Okay, so maximum a posterior or MAP estimation or estimator is actually turning probability to optimization. Like basic of inference coming from MAP estimator. So MAP estimator kind of changing probability to optimization problem. So that's amazing. So in other words, in maximum a posterior estimator, so MAP is, I didn't write that here, maybe I write it up. So maximum A posteriori, I don't know why they call it this, MAP. So MAP coming from this maximum a posteriori estimator. So we have posterior, this is posterior, P of x given z is posterior, x is unknown, is a state that we want to estimate, we want to find, and z is measurements. Of course, z is always used as a measurement. I don't know why they use z. So z is measurements. So measurements kind of noun. We know measurements. We measure them. We use sensors to measure them. And if we get argmax of that, if we maximize this probability, argmax, I mean find the x that maximize this probability, so that x is the optimal x. The best estimation, if you remember, we talked about that, the best estimation is a conditional probability. Oh, wait, I don't have this. I should hear you guys if you talk. Okay, okay. And if you want to if you have any question, you just can open your microphone and talk. I can hear, or you can type it up in a chat, and I will answer when I see that. Okay, so that's the maximum a posterior, and I think the maximum a posterior is a very simple way to solve so many problems. We can see that's amazing thing. Like for example, Kalman filter can go inside this. A slam problem can go inside this too. Simultaneous localization and mapping, and position estimation, weather estimation, path planning. What can I say? Everything. That's why knowing this maximum a posterior, and later on in this class we can see the maximum a posterior is very aligned with factor graph, and they are like friend together. They are going together easily, and they fit together easily. That's why we need to know maximum a posterior to see how we can get inference in factor graph optimization. So normally maximum posterior is changing a probability to optimization. What we want to get inference. Inference means something that we don't know about it. We want to estimate it based off the things that we know. What we know? Z. We know Z. Z is measurements. We know it. We measure it. But we want X. X is not known, but we know the probability of that. If we maximize that probability, we can get X out. We can see how. Okay, but it's not just that. We know Bayes rule. We know posterior density, P of x given z, it can be easily break down using Bayes formula. So how this can break down? So you can write posterior density, P of x given z is equal to, or maybe we just say proportion. We know right now what is proportion. Proportion to P of z given x, that is likelihood, likelihood of measurements, and P of X, that is prior information about X, prior about X, P. Okay, so we know that, but another things we know that log is not changing the trend of the function. So log is not change the function, but the things that we need to consider is that when we get negative log, minimization change, maximization changing to minimization. This is another trick in optimization. Anytime, because minimization is very well known, and this it's most of algorithms loves it. Most of algorithms working with minimization, not maximization. I don't know why, but it's easy to change from maximization to minimization. We just need to make objection negative. Easy. We make objection negative, and that become minimization. So, and we put log for another purposes. This log coming from there. Actually, another things that happening in this log of product becomes sum. That's amazing because it makes it linear. So when I'm talking about making that linear, means you can implement it with matrix computation. It's not just multiplication, even there is exponential family. The exponential family and log are friend too, because log of exponential are gonna cancel out each other. So that's another point that I want to mention. Imagine the likelihood is Gaussian, or prior is also Gaussian. So when I'm talking about Gaussianity, so if the measurements model, this is measurements model. So measurements model is a model to explain how we can translate from a state space to measurement space. So here we have a function h, that this function h translates state to measure. Measurements is noun, but we need to have a model for that. But the point is that this model is Gaussian if we consider the noise Gaussian. We consider the noise Gaussian. Gaussian means normal distribution. So in this case, we can write the likelihood of z in a Gaussian way. So we explained this, I think, last class as well. So here we have a Mahal distance. So we are talking like Mahal distance is sometimes called normal distance because it's normalize it using this sigma. So the sigma gonna go in between instead of just square it. We also normalize it, and this normalization is when you are dealing with distribution. You know, you want to find this distance between two different distributions. That's amazing. You can do it with Mahal distance. That Mahal distance is amazing. So anyway, here we have, you want to see how close this is your predicted measurements, and this is the measurements. You want to see how your predicted measurements is close to measurements, how close they are. How Gaussian works in that? Because in Gaussian, when this difference gets smaller, the probability going higher. So that's bell shape. When this gets smaller, this is the difference. This value, what we call it here, for example, carried like y. So when the y gets smaller, this is 0. When it gets smaller, this probability getting higher. That's why it makes sense to have Gaussian distribution for likelihood. Okay, so if you have that, it's gonna be amazing. What about prior information? If the prior is also Gaussian, so prior is p of x. So what that means, prior? Prior means what we know about x. How much we know about x. If we know a little bit about x, so the prior also can be Gaussian. So what is this part? This part is showing how much your model, how much your state is close to the mean. How much is close to the mean? Do you remember in Gaussian distribution? In Gaussian process. In Gaussian process, you had a distribution of the function, like for example, you had something like that, and you have a function, and you define this distribution in this function. So distribution means this how this function changing in this band is like a band, and how much this x close to the mean. So it means how much your estimation is correct, how much your state is actually correct, based off the previous information that you had that makes that mean, how much you are close to that. So this is also sometimes specify the motion model too. So you want to see, for example, the estimated value based off past information that most of the time, in robotic, for example, you can see, okay, if I was in that position before and I was moving in that speed, I'm gonna be in this position now based off the time, and finding the dynamic and velocity and acceleration, noise and stuff, we can estimate that. So anyway, this is normal way to explain prior information and actually measurements model. So if there is Gaussian, something amazing gonna happen. Put these two formula in here and here and get log. What's gonna happen? Log gonna cancel out exponential families, and the constant value is not important in maximization, so we can remove that too. Or because they are equal, we can take that out anyway. And what we're gonna get is this. This is beautiful. Why is beautiful? Because it's just sum of a square. Sum of a square of Mahal distances. Sum of a square is very well-known problem. So many algorithms are actually implemented for that, to solve that. This is very famous problem, like for example, Gauss-Newton method can solve that. Another method is LM method, that is Levenberg, Marquardt algorithm, and more. There is so many algorithms can solve this. So this is still nonlinear because you have a square, and is normalized square because it has like Mahal distance. We have covariance involved, but it's very well-known question, and so many algorithms can solve that. What else we can, so yeah, that's general idea behind maximum and posterior. Any question about maximum posterior? So maximum posterior is actually very good, especially if you have Gaussian measurements and Gaussian prior. I mean Gaussian measurements and likelihood actually. When it's Gaussian, most of the time Gaussian. If not, what we do? We can approximate it with Gaussian. You know, we did it a lot in our class. Do you remember many times we transferred some actually distribution by some function, and the result was so complex, and we said what we do, we say okay, let's find mean and covariance, so and approximate it with Gaussian. That works. In many cases works, and in nature normally so many phenomena are Gaussian. That's another thing that we can consider. However, there is methods that are not Gaussian and it's still solvable using maximum and posterior as well, but we need to deal with some complexity, because this optimization problem not gonna be simple to linearize. This can get linear easily. We can see that next class, not today. We're gonna see that how we can linearize that to, when I'm talking about linearize, just use matrix. You use multiplication of matrix and transformation, like multiplication and inversion. We have some invert as well, but because we have a sparsity, we're gonna talk about sparsity too. We can do that very fast. We can do that very optimal. So that's maximum and posterior. So maximum and posterior. Oh, the last thing that I need to mention is that each of these is kind of local residual. Local residual. Residual. Do you remember about residual? We talked about residual before. If not, residual is is different between predicted value and actual value. That's a residual. As you can see here, we have residual. Here we have also residual. And imagine you have many other factors. We're going to talk about factors. So they are residual. Okay? So this is maximum and posterior. I think that's enough for maximum and posterior. We're going to use that a lot. But we just need to know that this means done. If you have optimal value equal to arg mean of sum of a square, it means done. It can solve easily. Okay, that's very important. Okay, let's go for BaseNet. We talked about BaseNet last class, but we want to see, is it the BaseNet the best way? Is it the best graphical model for probability, or we have better one? We're gonna see that the BaseNet was relationship between children and father and mother and parents. Normally is not very good in robotics, in so many applications. We have a little mess in this between parents and children. I'm kidding, just so in BaseNet, BaseNet is good for data model. Yes, is because measurements are generative. So because of that, y is equal to h of x plus noise, for example. And this is a generative model of measurement. Oh, let's cut that z. So this model help us to find probability of x1, x2, xn is equal to product of some like probability of x1 given parents of, let's call it xi, parent of xi, or j, maybe j. Sorry. So this structure was BaseNet. We already talked about BaseNet. But in so many applications, okay, in this BaseNet, we also consider measurements unknown. That's questionable. We also consider measurements unknown because in here we have x1 and x2. This x consider x, z, l. Z is measurements, L is landmarks. Landmarks. Let remove landmarks for now. Okay. Let just consider x and z. In this, x and z are kind of equal. If you remember, in BaseNet we consider both of them as a state because BaseNet is like normal graph. We have states that can be measurements or x, and they are directed like this. Okay, so for example, let's fix that in a better way. Like you had like you have two fodder and x is from z1 and z2, for example, something like that. That was BaseNet. So consider measurements as a state too. But in so many problems, measurements are not a state. Measurements are noun. We know about measurements. We can measure them. How? Using sensors. We can measure them using sensors. So that makes a little problem for BaseNet. Okay? So in so many applications, specifically in applications like localization and mapping, that happen a lot in robotics, when the robots need to, they don't know where they are, but at the same time they found their position based off their surrounding, and they try to find their way to go, and at the same time do mapping. Mapping means find a information about the environment. This problem, that is very important problem in robotics, cannot be solved using BaseNet, because in BaseNet we consider measurements also as states, and also this relationship between parents and child make mess, kind of, and we don't have loop. That's another problem. We can't have loop here because it's cyclic, a cyclic graph. And directed. When you have direct graph, you have some limitation. So it's not nice. Is any other way to is another graphical model? Yes, there is. And that graphical model is factor graph. Another problem is also a sparsity. A sparsity is a little problem because in a sparsity, in actually BaseNet, so many things related to so many things. If there is so much relationship between things, this is not sparse. A sparsity coming, sparse coming when you have, like, this is a state and you are just related to multiple things. This is S2, for example, this is S3. You just related to multiple things, not too much stuff. This is a sparse. So in a sparse, relationship matrix that later we're going to see is called Jacobian matrix, J matrix. This J matrix is mostly zero. We have just some values around like this, and the rest zero. Because this Jacobian is the basic things in optimization. We can see that later. This Jacobian matrix in BaseNet is lots of value there. So it's not sparse, so we cannot solve the equation simply, linearly, fast. But in later on, we can see in factor graph, this is factor graph actually, I just draw it, factor graph. Instead of having measurements, we have factors. Okay, so we're gonna see that soon. So anyway, in the other method is factor graph in general. So the factor graph is actually directly going to posterior density, saying, okay, what about we just break down posterior density to multiple factors? In this case, these factors are actually some little information about the states. Some little information about the states. We call them factors. And each measurement can make new factor. And they are all together make a structure. So that structure called factor graph. Like for example, in a path planning, for example, you have multiple states, x0, x1, x2, they are states. Unknown, we want to find it, we don't know that. But we know that, for example, source and destination. In path planning, imagine we know source and destination. So we know some prior information. This is prior. Is a factor. We also know moving from this to this is a constant velocity, for example, or odometry. So we know this one too. This is also coming from odometry, so we can get acceleration and velocity and direction, gyroscope, and whatever sensor you have. And another one for this. We also can measure distance to the wall or the chair or whatever, obstacles. We can find these too. Amazing, isn't it? So we are defining a complex problem, path planning, using some states, x, and some factors, f. That's it. This is called factor graph. And that can solve so many problems easily. Kalman filter can go inside this. Islam can go inside this. Optimal control can go inside this. Path planning can go inside this. Gaussian process can go inside this. Can you believe it? Gaussian process is going inside the factor graph. So it means if you know factor graph, you can solve so many problems that years and years people were thinking, and it's still they teach them in a school in different things, you know, it's very complex problems. And you just need to know factor graph. And when you know factor graph, you can visualize them. And you know, visualize things is much easier. Oh, should put this to like visualize them. I don't know why I don't see my picture. Okay, maybe here is better. Okay, so I need to maybe talk about this. Oh, good. Got it. Now it's better. So yeah, you can visualize it. When you visualize it, when you can visualize the problem, you can solve problem much easier. And imagine this robot tomorrow add another sensor in top, like add another GPS in top. What gonna change in this structure? You tell me. Just another factor. Imagine next time use LiDAR, another factor for LiDAR. Nothing else gonna change. So it means how generative and general is this factor graph. So that's why it's so important for us to know that, especially when we are working in perception, robotics, AI, and anything related to electrical engineering. They all can go inside this. You know, I work in trust management between robots, and that go inside this. You know how, for example, two cars in a highway can arrange their speed together, or they can make a formation. When you are talking about multiple agents, they all can go in this. This is for one agent. You can draw another one for the second agent, and they are collaborating. How they collaborate? They just need to have another factor for collaboration. Loop closure. Do you know what loop closure means? Loop closure means when you are just dealing, you have a robot that just using, for example, odometry to go to somewhere. But odometry or IMU, for example, the problem with that is it has drifting. What drifting means? Drifting means you have additive error. Every time when you move, you add the error together. After 100 step, you are off the grid. You are somewhere else. You think you are somewhere, but you are not there. You are very far from there. So in drifting, one method of solving that is to make a loop. When you make a loop, when you see something that is familiar, say, oh, I saw that before. So you can correct your position based on that. Called actually loop closure. That can be solving that as well. Okay, so anyway, this is factor graph. Each measurements become a factor, not a variable anymore. We are separating variable actually from we separate unknown state from measurements and likelihoods, and that gives us a sparsity. The Jacobian matrix that we're going to see that later is going to get a sparse. Why it gets sparse? Because you're just not you're not related to everything. You're just related to multiple things around you. This is like a local things. You are doing local, but at the optimization, gonna do it global eventually. That is gonna be amazing. We're gonna see that. That's example of fact. Anyway, what is factor graph? Factor graph is a bipartite graph. Bipartite means it has different nodes. It's not just like BaseNet, just one state, measurements go there, everything go there. That sucks. We have different nodes. Some nodes are states, some are not states. And they are actually factors. So we have factors and states. States are empty circuits. Factors, we consider them as a fill objects. Sometimes we use circles, sometimes we use diamonds, sometimes we use rectangle, triangle, whatever. Filled is, and some factors are between two states. They are between two states, like for example, dynamic factor or odometry factors are between two states because make relationship between two states. And some factors are unary factors, because they are just like, for example, collision, obstacle avoidance. Obstacle avoidance is just unary, just give one measurements. Or prior information is just unary, like if you know the source, this is source and destination, for example. Okay, so this is factor graph. So factor graph can be written as a product of all factors. So if you have this problem, you can write probability. Here is G because it's for each function. Like in 2001, Xingshang was the guy that mentioned that at the like a first person that talk about that, and he talked about any function, but it moved to actually distribution function later and becomes amazing when you are dealing with distribution. And in distribution, this G gonna be P of X given Z, okay? And this is product of all factors. And what is these factors? These factors are little information about that state, that specific state, not all states. For example, this is position and velocity in time 0. This is position and velocity in time 1. Position velocity in time 2, for example, this one, in time 3 and rest. In this is for a robot, for example. So we have variable nodes, we have factor nodes, and we have edges. Edges are connection between actually a state and factors. So we don't have two states connected to each other. We don't have this. If two states wants to connect to each other, they need to have a factor. This factor defined how these two relate together, how they are related together. Like, can we say x1 is f x0, for example, plus something? That's why I'm saying that's a dynamic that's a dynamic factor. Okay, and these edges, but some factors are unary factors. Unary factors, like this is a function of just x0. This is the function of x0 and this x0 and x1, for example. Okay, so that's called factor graph. Let's do example. One very famous example, and most of the books talking about that when they talk about factor graph, is a slam problem. It's called a slam toy problem because it's very small. A slam problem coming from simultaneously localization and mapping. Like at the same time, two mapping and actually a localization. Simultaneous localization and mapping. Sorry for my handwriting. I should maybe make this like that. Okay, now I can write better. Okay. Okay, so simultaneous localization and mapping. So what we have in this problem? In SLAM, we have a robot. SLAM is for robot because robot needs to simultaneously localize itself and find the map. So we have some states. We have states. We have landmarking. Landmarking are just reference points. We have prior information about landmarking and states. Prior information means some information about landmarks. For example, we know they have color, red color, okay? Or for example, they are the edge of the building, whatever. Also about X, we have some information, like we know where is the source? Where is destination? That's a prior information. About motion model, we know how we are moving from one state to another state. That's coming from like odometry measurements, like we have sensors, IMU, for example. Oh, yeah, IMU, odometry or IMU. And relationship between the state. And also we have measurements that, for example, we read, we access to closest obstacle. We have some bearing sensors, range sensors, like like for example LiDAR. We have that. So we have bearing or range sensor as well. So this gives us obstacles around us or distance to actually landmarking. So we have this. Can we write this up as a one optimization problem? Yes, we can. How? Like that. Done. So we can write the huge problem. A slam problem is one of the most complex problems for robotics because the unknown is not just a state, but landmarking is also unknown. We just know some information about them, but we don't know their position. But we can find that. So as you can see in this problem, landmarking and X are both unknown. And Z is known because it's measurements coming from sensors that we said, IMU and whatever, bearing, range, and so forth. So we can break down to multiplication of some factors. That's it. Factors, we have prior factors, we have landmarking factors, we call them unary factors. We have odometry function, double factors between two neighbor states. And we have other measurements factors like distance from landmarking. We just multiply them all together. So what's the next? Maximizing this and make minus log and change multiplication to addition. And if we are lucky, if these distributions are Gaussian, even the exponential is going to get disappear, and it's going to change to sum of a square and can be solved easily. Okay, so because we don't have time, let's go. Yes, it's going to change to MAP. That's why I talk about MAP first, to see how this is amazing. Lots of applications, especially in robotics, when you want to have optimal estimate. Optimal estimate is always coming from fusion. Look at how many sensors you can add to your robot. Camera, radar, LiDAR, GPS, name it, whatever. You can add them all together. All of them can just be one factor. One factor for IMU, one factor for LiDAR. And what about tomorrow I add another factor? You add another factor, another sensor. You just need to add another factor. So it's so general. We can do inference easily because using maximum and posterior. And we can solve it easily because it's very well known. Gaussian Newton, how many years ago they developed the algorithm for that. And developing new algorithms and so forth. Okay, so that's very general. Compared to BaseNet, we need to mention why this is better, especially for our application. First of all, is based of constraints. So all of these things that we mentioned is constraints, like IMU, like LiDAR. Why is constraints? Because we are kind of finding residual. Remember, we're finding residual. We wants to optimize some constraints in this between. So this constraints optimization is very aligned with factor graph. Scale efficiently because it's sparse. Scale efficient. We can scale it. It works nice. Support nonlinear least square. because MAP optimization is non-linear, so it can actually support that. Handle loop, that's amazing things. Handle loop has a problem in BaseNet because BaseNet is a cyclic graph, but in factor graph it can be handled easily, and you can easily add any other sensor you want. This is the SLAM problem in real world. You have a robot moving and detecting obstacles around it, and obstacles, landmarkings, for example, in table and chairs. Can we model that with factor graph? Yes. How? You just need to consider states. In the next page, I'm going to show that. You need to consider states and landmarking and implement it with factor graph. You have some prior information, some measurements that coming from distance to landmarkings, and define it as a factor graph. Next class, I'm going to write the code for that, and you can see how easily you can write a Python code and solve it. Amazing. It can actually generalize so many problems. Just break them down to the factors. But yes, that's the point. Maybe you ask me, okay, so not everything can break down to the factors. That's the point. Yeah, that's the point. But still, we can approximate it to the factors. So, and like for example, you say, okay, we want to find, as far as we can measure some factors, that's enough. If we have extra factors coming up, we can add them later. For many applications, like especially in robotics, SLAM, estimation, path planning, we can use that very nicely and find and give you actually optimal solution. Maybe is approximately optimal because we are considering Gaussian as we assign it Gaussian. So anyway, this graph is bipartite, and this is loss of application. Next class we're going to talk about more about factor graph optimization, and talking also we have another topic to talk, that's hypothesis testing. It's very simple things. We're going to talk about that too next